Hello everyone, I hope everybody is fine and happy and everything is fine. Welcome to a series of lectures on the topic of limits in calculus. So in this lecture we just want to know what is a limit in calculus, limit of a function. So introduction to limits, it says the limit of a function f of x as x approaches a, and a is just a number, it could be like 2, 5, whatever, equals L, which is another number, if we can make the values of f of x arbitrarily close to L by taking x to be sufficiently close to a but never equal to a. That's the official definition of limit of a function. And in terms of notation, we just write limit of f of x. We use LIM, which stands for limit of f of x when x approaches a equals L. That's the short form of writing what it was stated above. So it tells us that the value of the function f of x will become extremely close to this number L if x becomes extremely close to this other value of a. So we say limit of f of x when x approaches a equals L. Now, that's perhaps a little bit theoretical, and in practice, by showing you an example, I'll try to explain what the idea of limit is. So here we have a very simple function, a linear function, like y equals mx plus b. It says 2x plus 10. We want to show that limit of 2x plus 10 when x approaches 1 is equal to 12. This 12 is that capital L mentioned earlier, and this 1 plays the role of lowercase a. We said x approaches a before, now we say x approaches 1, which means that x becomes very close to 1, such as 0.999, for example. And 2x plus 10 is just our linear function, which can be, of course, any function. It could be logarithmic function, polynomial function, rational function, trigonometric function. Any kind of function is possible to be instead of f of x. So I'm selecting some values of x arbitrarily, and I select 0.5, okay? I'm just investigating what is the value of f of x if x is 0.5. So f of x is 2x plus 10. It's a linear function. So let's say y is equal to 2x plus 10. Now, if x is 0.5, okay, or 1/2, then 2 times 0.5 is going to be 1. 1 plus 10 is 11. So f of x will have a value of 11 if x is exactly equal to 0.5. Now, if x is not 0.5, and if it is 0.9, for example, then 2 times 0.9 would be 1.8. Add it with 10, it's going to be 11.8. So we're saying that the value of y, or the value of f of x, if x is exactly equal to 0.9, is exactly equal to 11.8. That's what we're saying. If x is 0.99, okay, which is like, you understand, it's very close to 1, obviously. If that is the case, then 2 times 0.99, we can even use a calculator. 2 times 0.99 plus 10, it would be actually 11.98. So 11.98. So we are saying that if x is equal to 0.99, the value of y is equal to 11.98. Now I select an x value which is like much closer to 1 actually. It's not equal to 1. I never said it is. 0.9999. If that is the case, so we're going to use the calculator. So it's going to be 2 times 0.9999, as I said, and then plus 10. The answer will be 11.9998. So 11.9998. So you see what is happening here most likely. As I select x values that are closer and closer to 1, the values of f of x, or the values of y, become closer and closer to some number. And I think you may already guess what that some number is. 11.9998 is very close to some number that I don't mention, but you may know what it is. Now, the thing is that I selected values of for x that were less than 1. I can also select values of x that are more than 1. For example, 1.5. If you plug in 1.5, 2 times 1.5 is 3 plus 10 is going to be 13. So that's the value of y. We are saying if x equals 1.5, then y equals 13. That's what we're saying. 1.1 is the next value I have selected in my table of values. 2 times 1.1 is 2.2. Plus 10, it's going to be 12.2, right? 2.2 plus 10, 12.2. So we're saying if x is exactly equal to 1.1, then y is equal exactly to 12.2. 1.01 is another value I selected. I know you might have noticed the trick I'm using here. 1.01 is a number that is very close to 1 actually. It's a little bit more than 1, but it's close to 1. So I'm going to plug in 2 times 1.01, and then I'm going to add 10, and I get the answer of 12.02. 12.02. So we're saying that if x is 1.01, then y is 12.02. Now here, on purpose, I'm going to select a value that is very, 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 very close to 1. It's 1.0001. Okay, I'm going to plug in there to see what is the value of y. So I end up with 2 times 1.0001, and then I'm going to add 10, and sure enough, the answer is 12.0002. Okay, so we're saying if x is equal to 1.0001, then the value of y is equal to 12.0002. That's what we're saying. Now, when you look at this trend, finally, we are saying the following. We are saying if x approaches 1, I never said equals 1, and I will never say it's equal to 1. I'm saying if x approaches 1, which means that x becomes extremely, extremely, extremely close to 1, such as 0.9999, or such as 0. You put like 200 nines. You understand what I'm saying? If x approaches 1, if it becomes extremely beyond your imagination, close to 1, then the value of y will become very, very close to actually 12. All right, that's what we're saying here. And we write it like this in order to communicate our idea, our new concept of limit. We're saying that the limit of this function 2x plus 10 when x approaches 1 is equal to 12. What does that mean? It means that if x becomes extremely, extremely close to 1, then the value of y will become extremely, extremely close to 12. That is what we are saying here, okay? And this arrow you see is not equality sign. It is read as x approaches 1. It means that x becomes very, very close to 1. That's what it is. So the limit of a function, f of x, I selected a linear function. It could have been a rational function. It could have been a polynomial function, whatever function. The limit of a function, f of x, as x approaches a, in this case, x was approaching 1, if you recall, equals L, in this case, it was 12. If we can make the values of f of x arbitrarily close to L, which means close to 12, by taking x to be sufficiently close to a, which means sufficiently close to 1 in our example, but never equal to a, which means never equal to 1. And I said it earlier that I'm not saying x is equal to 1. That's the delicate difference between the limit and the value of a function. See, if I write f at 1, so this is f of x, right? F of x is 2x plus 10. If I say what is f at 1, well, you can plug in 1 and you're going to say the answer is 12. So this is not a secret. F at 1 is equal to 12. Who says no? But you have to know the difference between the ideas here. When we say f at 1 equals 12, it means that x is solid equal to 1. And if that is the case, y, or f at 1, is solid equal to 12. That's what it means, okay? But in limit, we're not saying that. I know you're going to say, well, it's the same number. Yeah, it is the same number, but that doesn't mean anything. It is the same number, sure. But the idea, the concept of limit is different here. When we say limit of 2x plus 10 when x approaches 1 equals 12, that doesn't mean at all that we are talking about evaluating a function at a number. We are not doing that. We're not saying that f at 1 is 12. Sure, everybody knows f at 1 is 12. But here we are saying that if x becomes extremely close to 1, then the value of y will become extremely close to 12. That's what we are saying here. And we never ever say that x is exactly equal to 1. Here, we do say x is exactly equal to 1. We're not joking here. We say if x is 1, y is 12, period. But here, we're not saying that. I know, apparently, both numbers are the same, but you have to understand the delicate difference between the ideas here, okay? Now, you notice that I selected x values that were less than 1, and I also selected x values that were more than 1. But in any way, I was picking these values on purpose such that the value of x becomes closer and closer to 1. So when x approaches 1 from right-hand side, from values that are greater than 1, we use this notation. We say x approaches 1, and we put a plus sign on top corner. Top right-hand corner, you put a plus sign. It doesn't mean that 1 is positive or negative. It means that x is approaching 1 from right-hand side. So this is right-hand limit. And we saw what happened to the answer. The answer was like 12. Now, if you write x approaches 1 and you put a little negative sign at the top right corner of 1, it doesn't mean that 1 is negative. It means that x is approaching 1 from left-hand side. Okay, LHL, left-hand limit. So left-hand limit of 2x plus 10, when x approaches 1 from left-hand side, that's the meaning of this little negative sign you see there. From left-hand side, you saw what happened. The answer was still 12. And you may finally say the same thing that you said before. In general, when you say x approaches 1, it could mean either way. When you say x approaches 1, somebody might say, okay, is it approaching from right side or left side? Well, you're going to say both. If you have this intention of x approaching 1 only from one side, only from right side, let's say, you must write 1 plus. Or if you want to discuss a situation where x is approaching 1 from left-hand side only, you must write that negative sign at the top. But when you don't write anything, it means that it could mean either way, all right? It means, like, generally speaking, when x approaches 1, it doesn't matter from right side or left side. But if you want to be specific, then you have to put the plus or minus sign at the top right corner of 1. Okay, so I hope you understood the idea of the limit, okay? We will be talking about limits a lot, believe me, a lot. But here, I just wanted to explain the idea of the limit, okay? And I hope you understood that despite the fact that we get the same answer of 12, but we are doing a different thing here. We are saying a different thing here. We're not evaluating a function at x equals 1. That's not what we're doing. And these limits have some properties, standard properties. There is like 7 of them out there. It says if limit of f of x when x approaches some number c equals L, capital, and limit of g of x equals to m when x approaches c, then we can say the following. These are properties of limits that we accept their truth without proof. Okay, they're known as properties of limits. And many of them are like common sense. You may say, why did you even mention this? It's obvious. Limit of the sum or difference of two functions, limit of f of x plus g of x, or even f of x minus g of x, when x approaches c is equal to the sum or difference of the limits. So limit of f plus g is limit of f plus limit of g. In other words, L plus m, all right, when x approaches c. And if it's difference, you just put minus in front. So you may say, well, it makes sense. It's common sense. Well, yes, it is. That's what we're saying. But this is a property that is out there. You can use it. Limit of k times f of x. And k is just a real number. I'm going to say k belongs to the set of real numbers. Let's say 2. 2 times f of x equals 2 times limit of f of x when x approaches c. So it's going to be equal to k times L, because what L is limit of f of x when x approaches c. So here we're saying if you have a function f of x that is multiplied by a constant like 2 or 3, and you're taking the limit of that, you can take the limit of the function separately and at the end multiply by that so-called 2 or 3 or that k value, whatever it is. It's called constant multiple rule. The first one is called sum and difference rule. Okay? So sum and difference rule, constant multiple rule. This one, it says limit of product of two functions is equal to the product of the limits of those two functions. So limit of f times g is equal to limit of f times limit of g. In other words, L times m. This property is called a product property, or you can say product law. Okay? Limit of a quotient of two functions when x approaches c equals to the quotient of the limits. So limit of product equals product of limits, we said. Now we say limit of a quotient equals to the quotient of limits when x approaches c, obviously. So the top is L, the bottom is m. And whenever you talk about any kind of fraction, you should always bear in mind that the denominator cannot equal to 0, obviously. So m cannot equal to 0. Limit of a power this time, we have f of x raised to the exponent of n. And n is a positive integer, like 2, 3, 4, 5. When x approaches c, that limit is equal to the limit of the function, whatever the answer is, raised to the exponent of n. So limit of a power equals power of a limit, basically. And that is equal to L raised to the exponent of n, because L was actually the limit of the function separated by itself. If the limit is 12, and then you're going to raise that 12 to the exponent of n, whatever the n is, that will be the final answer. So here we're saying that limit of a power equals the power of the limit. And then here, finally, we say that limit of the nth root of f of x, it could be cube root, fourth root, or square root, when x approaches c, is equal to the nth root of L itself, or in other words, L to the exponent of 1 over n, if you express it with a rational exponent. Again, n is a positive integer. So we're saying that limit of like cube root of f of x, for example, is equal to the cube root of the limit of that function f of x when x approaches 0, calculated separately. That's what we're saying here. So standard properties found in any standard calculus textbook are the 7 properties of limits. If n is even, like you're talking about the fourth root or square root, we assume that L is positive, obviously. This is a technicality issue because you can't take the square root of a negative number. Square root of -4, we don't know what it is. Your calculator cannot calculate that. Now, some people, of course, mention about imaginary numbers, but that's a different story. That's beyond the level of this course. Okay, so we discussed, and this one, I have to erase it. I don't know why this is here. It must have left here from past lecture. I just noticed. So we discussed the 7 properties of limits, which I'm going to use in future, actually, to solve some problems. And we try to explain the idea of limits just to begin with. In the next lectures, we will do some solved examples. I'm going to show you some examples where I will be using these properties of limits, which we accepted them as a fact, and then we will learn more advanced stuff later on, but one at a time, okay? And I highly recommend that you watch these video lectures multiple times. You pause these videos you watch, you rewind, you watch it again, and then you pause again, you take notes, and then you play again, and you watch and then pause, read the question by yourself. So it should take like more than 1 hour just to watch a short video. If you watch it several times, multiple times, due to time restrictions I have to explain things sometimes much faster, but you have to give yourself time by just pausing the videos and thinking about what you heard, what you saw, what you learned, what you copied, and then maybe watch it for the second time, then you understand a little bit better. You watch it for the third time, you even understand much better. There were things that the first time you watched, you didn't get it 100%, but third time you watched, and then the fourth time and fifth time, I'm not joking, fifth time you watched, now you fully understand what is going on. By watching once, you're not going to get anything. You will just know we're talking about like functions. But if you watch it like several times, multiple times, and you think about what you saw, and you try to read the questions, then you will understand things much better. It's very natural. Okay, thank you very much for your attention, and we'll see each other again.